Now we will try to address convergence in Markov chains. The state space of a Markov chain can be uniquely partitioned into a set of transient states and then a number of irreducible recurrent classes. There is a result that we can prove which says that if the state space is finite, then at least one state has to be recurrent. And all the recurrent states, no matter how many, are non-null. This basically says intuitively that if there's a finite number of states, if there's a finite state space, you cannot get lost forever. You cannot, there's nowhere to escape. Eventually, you will return at least one state. At least there will be at least one recurrent state. And similarly, remember in the case of a null recurrent state, the expected time to return is infinite, but that is not going to be possible when the total number of states is finite. Okay, so the proof is then very easy. Suppose the contrary. Suppose all states are transient to reach contradiction. Then the limit as n goes to infinity summed over all j pjj of n must be 0, but this is also by definition equal to 1 because I'm summing over the whole state space. This is a contradiction. This means that there's at least one recurrent state. All the states cannot be transient at the same time. Non-nullness, the second part of this lemma, I leave this to you as exercise. Now let's see some examples and let's see what happens in a recurrent class as time goes on. So let's take a look at this example of a Markov chain with a finite number of states. State 2, from state 2 you can go to 1 or you can go to 3. 1 is an absorbing state and 3 and 4 are a recurrent class among themselves. So 3, 4 form a recurrent class. 1 forms a recurrent class by itself. It's also an absorbing state. And 2, what is 2? 2 is transient. So this is an example of this partitioning where T, the set T, includes the state, where the set T includes the state 2 only. C1 is made up of state 1. C2 is made up of states 3 and 4. Now let's take a look at what happens to the probabilities Pii of n as n increases. So P11 of n. It is clear to see that P11 of n is equal to 1. If we start in 1, we will always be in 1. How about P12 of n? That is 0. P13, 0. P14, 0. How about P33 of n and P23 of n? Now, to answer these questions, I need to have numbers on these arrows. So let's assign some transition probabilities. Suppose all the transition probabilities These are 1/2, 1/2. And let's have these two transition probabilities also be 1/2, 1/2 for state 3, 1/2, 1/2. Everything is nice and easy. Now, if I'm in state 3, I'm going to be back in state 3 again, or in state 4. It is easy to show by taking the matrix, the transition probability matrix P, and raising it to the nth power, that this is going to converge to 0.5. Okay. Similarly, P44 and P43 and P34 are all going to converge to 0.5. Now, how about P23? P23 also, now P23, if I start in state 2, I will either get absorbed in state 1 or get absorbed in this recurrent class. I get absorbed in this recurrent class or this recurrent class by with equal probability, obviously from these two 1/2s. Now, if I end up in the recurrent class of 3 and 4, then the probability that I'm eventually at some point in the future in state 3 is equally likely between 3 and 4. So then it makes sense that P23 is going to converge to 0.25. Similarly, P24 converges to 0.25. So the matrix P to the n, if we summarize all of these together, the matrix P to the n, P1, 1, P1, 2, well, this is the first row. P2, 1, 1/2, P2, 2, 0, P2, 3, 1/4, 1/4, and then P3, 2 is 0, P3, 1 is 0, 1/2, 1/2, 0, 0, 1/2, 1/2. So this is the eventual probabilities of being in certain states depending on where we started. So this row corresponds to the different probabilities of where we will be given that we started in state 1. This row refers to the probability of being in each state eventually if we start in state 2. And this is if we start in state 3, this is if we start in state 4. So observe that in this case, there is convergence because there is no periodicity, but there are two recurrent classes, and this causes the existence of multiple steady state probabilities. Okay, so here is an important fact that is a theorem, of course, but we're not going to prove it in this lecture. If the recurrent classes in a Markov chain are all aperiodic, then the Pij of n's converge as n goes to infinity. They converge. They converge to numbers pi ij that depend on the starting state, possibly, and they depend on the eventual state j. So the probability of being in state j eventually, given that I started in I, converges to some value pi ij. And this convergence is going to happen if all the recurrent classes are aperiodic. Further, if there is a unique recurrent class, if there is only one recurrent class, then these numbers, these probabilities pi ij, do not depend on I. They can be represented as pi j for all I. So it doesn't matter where we start, there is a unique steady state probability of being in state j. So think of this example. This example has two recurrent classes, so the pi ij's depend on I. Let me give you a final example for this lecture where there is a unique steady state. Let's construct a very simple Markov chain with a single recurrent class. Suppose these are the transition probabilities: 0.8, 0.2, 0.5, 0.5. Okay. Now, if you take the matrix P, which is 0.5, 0.5, 0.2, 0.8, and raise it to the nth power, as n goes to infinity, you can show that this will converge to, let's call this P infinity, if you will, to 2/7, 5/7, 2/7, 5/7. So what does this mean? The probability that after an infinite number of transitions, I'm in state 1 is 2/7. The probability that I'm in state 2 is 5/7, and that does not depend on my initial starting state. Okay, so in the next lecture, we will talk about how we arrive at these numbers without taking p to the infinite power. Let's see if there's a systematic way of writing equations that we call global balance equations that can give us these eventual steady state probabilities in a ergodic Markov chain.